Dave's going to be presenting today, getting started with F#. He's a senior software engineer at Compare the Market. It's our agenda for the evening, also at the introduction stage. So it's only take a few minutes, and then we'll let Dave get started at 7:10ish. Dave tells me that this presentation will take about an hour, have a break at about 8:10, and then we'll come back for questions and answers. So just some meeting rules before we get started. So please, can we all respect each other and their ideas? Please, could you also go on mute during presentations? If you disagree with what has been said, please challenge politely at the end of the presentation. These meetings are not for recruitment purposes, and also got zero tolerance towards discrimination of any kind. And then just lastly, before I hand over to Dave, our next .NET Meetup date is Tuesday the 30th of November. Obviously at that point, .NET 6 will have been released. We'll have highlights from .NET Conf 2021. And with that, Dave, take it away.
I'm Dave Cook. I'm a senior engineer at Compare the Market, and today I'm going to give you an overview of F# and hopefully give you both the desire and the tools to get you started. I'd like to try and answer questions at the end if that's okay, because I've got a lot to cover tonight. So I'll share a URL to a repo with all the slides and the code. Before that, just a little bit about me so you know where I'm coming from. I probably describe myself as a predominantly .NET backend dev, although I do dabble with Node and Python from time to time. I've spent the last 5-ish years building and maintaining a suite of microservices in .NET Core, C#, Docker, and Mongo. And before that, I used the .NET framework in a variety of ways, including VB.NET, WCF, and web forms. More recently, though, I've used F# and functional programming, which is teaching me new ways of thinking and new ways of approaching problems. And I found it to have a profound impact on the way I write code when I'm not writing F#. So I came to F# via a perfect storm of luck and frustration, really. A while ago, I was teaching myself Node and JavaScript, and I was getting more and more frustrated. And it was partly due to the developer experience and things like poor IntelliSense, but mostly with the language itself, or what I should really say is with how I was trying to use the language. I now realise, having learned some F#, that this was all down to me and how I was approaching things, and that trying to translate object-oriented C# into JavaScript and expecting the same experience was probably a mistake and tainted my experience. So frustrated, I put down Node and looking for something else. Decided to spend the last of my training budget on something different. So I was browsing through the Manning's book catalogue and came across this real-world functional programming co-authored by John Skeet. Now, I'd read C# in depth and I'd learned a ton, so I was sold. The book arrived, and honestly, I couldn't put this thing down. I was hooked from day one. To be honest, I couldn't even tell you what I learned from this book because I didn't even finish it before I ordered Get Programming in F# by Isaac Abrams. And ever since then, I've been moving more and more in the direction of functional programming, applying functional techniques to C#, Python, and JavaScript, and teaching myself F#, which is how I'm here today. And before we go on, I feel compelled to say that I am by no means an expert in F# or functional programming. I don't use F# in my day job, unfortunately. Well, maybe a few cheeky additions here and there, which I'll explain in a moment. I'm an enthusiastic hobbyist or an advanced beginner, really. I've never built a production app in F#, and most of what I know comes from reading books, watching talks online, and playing with code in my spare time. So the aim of today's talk is to get you interested in F# and give you a taste of what it can offer, and hopefully give you a bit of a boost in starting your own F# journey. What is F# and what can I use it for? F# is Microsoft's functional first flavor for .NET. It's a general purpose, cross-platform, statically typed programming language that can be used for anything from web API, desktop apps, NuGet packages, console applications, global tools, and even scripting. It's actually possible to go full stack using just F# to build both the back and the front ends using things like SafeStack, Stable, and Bolero. which transpile to generate your JavaScript from F#. It's also possible to write all your automation to manage your build and infrastructure that can be written in F# too. So F# is not just for data science, machine learning, and pure maths, as you may have heard. So as with the .NET runtime, it's open source. It's been around since 2005, so it's a stable, mature platform. And the latest version is currently F#5, which was released last year with .NET 5, and version 6 lands with .NET 6 this month. And because it sits on top of the .NET runtime, it runs in your favorite IDE, will run everywhere you currently execute .NET code, including Docker, and it's already installed on your machines, so there really isn't any excuse for you not to give it a go. Not only that, but it's also interoperable with other .NET languages because it compiles down to intermediate language. So you can continue to use your favorite packages from NuGet, and you can even create hybrid solutions containing multiple .NET languages. So you can consume F# from C# and vice versa. So a couple of those cheeky ways in which I've used F# at work is to create an F# project for defining record types and then consuming those records from within C#. So this was prior to C#9. So if you're not lucky enough to be using C#9 yet, but you want access to record types, then you can do this now because these have been available for ages in F#. I've also created F# projects to house some property-based tests that validate the implementation of C# projects. I could have done this using C#, but I actually found that the examples on the web and the documentation for F# were more comprehensive, a little easier to do because of something called a computation expression. I won't be talking about property-based testing or computation expressions today, as they're probably both talks in their own right, but feel free to reach out if you want to know more. So I said that F# is Microsoft's functional first for .NET, but what does that actually mean? Well, in a similar way that C# supports OO and functional styles of programming, F# supports both paradigms too, giving you the flexibility to use either or both. But while C# leans in the direction of OO, F# leans more in the direction of functional programming. So you could describe C# as object-oriented first. And here's a diagram taken from Get Programming with F#. We can see C# and F# sit roughly on the axis of pure OO to pure functional programming. I say roughly because recent additions to C# has had it in moving over towards the right for quite some time now. So what is functional programming? Functional programming takes a different approach to object-oriented programming. In OO, the focus is on encapsulation or data hiding. So objects store state or data internally, and then expose methods to access or mutate that data over time. Data and behaviors are coupled together by design. But in functional programming, the opposite is generally true. So data and behaviors are deliberately decoupled. And instead of objects working together with other objects, functional solutions are built from functions that generally pass data in, returning different data out, with lots of small functions composed together to build larger functions, composed together to build applications. Now, at the heart of functional programming lie three core principles which F# embraces, and they are immutability, expressions, and first-class functions. So immutability means that once a value is created, it can never change. And if you've only ever written code that utilizes state mutation, this probably seems like a bit of a strange concept. How do you get anything done if you can't change anything? But actually, this is really useful because it eliminates all sorts of weird and wonderful bugs that can only ever happen because of mutation, such as race conditions. Everything is an expression. Every operation in F# returns something, a result of some type, or something that you can then use or do something with. There are no void types, and there are no if statements. In fact, there are no statements at all. And in many cases, there is no null. So this all aids code composition, which we'll soon see. And first-class functions. Functions are cheap and easy to create with low ceremony and can be used as values, passed as arguments, returned as a result from other functions, or stored in data structures. And as we look at the code, you'll see that F# makes this principle look like an understatement. You can probably see already that functional programming is quite different from the core principles of OO and what we as C# devs are used to. So, a word of warning. Given the principles of functional programming are fundamentally different to OO, it's worth pointing out that you'll be learning more than just a new language and a different syntax. It's a different paradigm, which requires a different way of thinking. Don't make the mistake I made with JavaScript. You can't approach this with the mindset of translating the code you would write in C# into F# syntax, as not everything is a one-to-one mapping. So my advice is to approach this with an open mind in the same way you learnt your first programming language, with curiosity over preconceptions. Now, with that little warning out of the way, here's a little code to ease you in gently, something you're hopefully all familiar with, well within your comfort zone. It's a bit of link. So here we have a method that takes in a number as an argument and uses that number to generate a sequence. Filter the sequence to find all the odd numbers, square them, and calculate the sum total. This is functional programming. Let's look back at those three core principles. So first-class functions, where and select are themselves functions, which take other functions as arguments, allowing us to plug in our own behavior and achieve different results. Our lambdas are complete functions, easy to create and use, easy to compose, and supplied as arguments to other functions. This is the same expression refactored to use existing functions instead of lambdas. Everything is an expression, so enumerable.range produces a result, in this case a collection of 10 integers. The where function takes the original collection and then returns a new collection. The select function takes a collection and returns a different collection. Sum takes the result of the select and adds the values together to return a total. Finally, immutability. Once a value is created, it can't change. Each of these functions takes in input and uses it to generate its output, but in each case, the original value is unmodified. And if we inspect the intermediate values in this version of the code, you'll see that the original values remain unmodified after the subsequent actions execute. So if you've ever used LINQ, then you're already familiar with some functional programming techniques. Right, let's start looking at some F# code now. What I'm going to try and do is show off some of the features that I think make F# a language worthy of your investment by showcasing the ways in which it can make our lives as devs easier. And some of the highlights, I think, include a powerful type system with the feel of a dynamic language, safer, less error-prone code. We'll write less code and tests, but still have a high confidence that our application is correct. And we'll favour simplicity over learning loads of different design patterns. We covered that F# is built on top of the base common library. So we already know our common data types such as decimal, ints, datetime, strings, etc. And we already know that it's a strongly typed language like C# or Java rather than dynamically typed like JavaScript and Python. However, F#'s compiler is incredibly powerful and is able to infer what type things are without the need for us to explicitly specify those types. So here we can see two functions, square and add. Square accepts a single argument, x, and returns the result of multiplying x by itself. Add accepts two arguments and returns the result of multiplying the two together. We've not actually declared any specific type information, but the compiler inferred from what we're doing that all the input arguments are integers. And as a result, return types are also integers. You can see this highlighted by our IDE, just above the function declaration, the type signature of the functions. It tells us that the square takes in an int and returns an int, while add takes in an int, followed by another int, and then returns an int. So the compiler is able, in most cases, to tell which types are required when calling a function, even though no types are specifically declared. This means the code we write is lightweight with low noise. And of course, it's type safe. So if we try to invoke the function with the wrong type, we get a compiler error. This is particularly useful when we create higher order functions or functions that accept other functions as inputs or return functions as outputs, something you'll be familiar with if you've ever used the func or action delegates in C#. So here we have a function called generate n items, which takes in two arguments, f and n. And above the function declaration, we can see the compiler has inferred from what is going on in the body of the function that f is a function indicated by the brackets that accepts an integer and returns a generic type of a. You can think of the a as the t that you would refer to when using generics in C#. It's also inferred that n is an integer, that the result of this function is a list of a's. So how has it inferred all of this from the two lines in the body? Well, line 1 generates a list of integers from 0 to n. So it's worked out that n must be an integer from there. It then pipes the list of numbers that's just generated into the list.map function, which is similar to link's select function. So it's applying the supplied function to each item in that list. Therefore, the input argument for that function must also be an integer. There's no explicit return needed in F#, so the last line of the function is the result that gets returned to the caller. So the result of this function is a list of a, whatever a is. That will depend on the supplied function. You can see that there's a lot going on here with very little noise to distract you. And this declarative style allows you to write code that says what it is doing without getting lost in the detail of how it's actually doing it. Here's our function being invoked on the last line. We supply it with a function and the number 20 as our inputs. And if we inspect the signature of the random number generator function, it does indeed require a single integer argument as an input. And the output, well, it doesn't really matter as the requirement was generic, but for our concrete type, it's also an integer. And the result of the function call stored in numbers is inferred to be a list of integers, which matches the inferred response of the function, which was a list of a. And we still have type safety. So if we try to pass this implementation of random number generator to our generate n items function, then we'd get a compiler error telling us that the type of the input argument doesn't match what's expected. So hopefully this demonstrates that F# gives you the best of both. The safety of a strongly typed language such as C#, as well as the lightweight expressiveness of a dynamic language or dynamically typed language like JavaScript or even Python. Before we move on, if we zoom out a little, take another look at those add and square functions, you'll notice they don't actually belong to a class. They simply live in the maths module as entities in their own right. So calling them is low ceremony, as there's no need to instantiate anything or refer to a type to which they belong. We can actually remove the maths prefix from this call site here in this example. You can see them grayed out on lines 10 and 11, as we've already added a reference to the module where they live. Let's delve deeper into the type system now. On top of the .NET BCL, F# has what is known as an algebraic type system, which might sound a bit mathsy and scary. It's not. I'll borrow Scott Bloshin's alternative name for it. He calls it a composable type system. And what he means by this is that you can compose smaller types together to create larger types, and that you can compose those types together to create even larger types. Now you might be thinking, okay, well, I do that with objects. However, the algebraic type system provides two ways to compose types together, which Scott describes as AND types and OR types, or choice types. So our AND types are things like tuples and records, which you're hopefully familiar with from C#, where you can say that a coordinate is represented by both an X and a Y value, and a person is a combination of an ID, a first name, and a surname. Choice types, on the other hand, are implemented using something called a discriminated union and allow us to say that a value or result of an expression can be one of n options. So this allows us to say, for example, that a contact method is a choice of either a phone, an email, or a post. Each of those options can have its own accompanying data specific to that choice. So here you can see that email and phone choices both have data on the right, supplied as strings, while the post choice has data defined with a list of strings to hold an address. And we can compose and or types together like so. So here we have a person defined at the top using a record type, which is a combination of first name and surname and contact method, which is a choice type. And then below, we create 3 instances of this type, each with a different contact method specified. So our first instance, Dave, we've set the contact method to the email choice. So the accompanying data is a string holding the email address. Graham would prefer to be contacted by phone, while Ross is going with snail mail. So the data provided is actually a list of strings representing the various address parts. As you can see, the algebraic type system provides us with a completely different way of modeling our problem domains. If you wanted to do this with objects, how would you do it? Would you build a God object with 3 contact methods as different properties and a flag indicating which property to use and store null in all the others? No, we'd probably use some sort of inheritance structure or an interface with multiple different implementations. The God object comes with the high probability of error in the form of null reference exceptions, while also allowing multiple invalid states, such as setting the flag for email as the preferred contact method, and then storing the phone number instead. Inheritance creates a lot of code, and there'll be dragons with inheritance that we try and tend to avoid. While the interface option creates a layer of indirection, it can actually make it difficult to work out which implementation is being used at runtime. And neither option scales particularly well or in a way that helps us fall into a pit of success. So let's say we introduce more options for preferred contact methods, say Twitter and Facebook. The God object is now a monster, and the problems mentioned before are much worse. The inheritance and interface options add yet more code scattered about the place, but the type system doesn't do anything to help you integrate your new options or point out where you've forgotten to do that integration. Let's do this now with F# and see how we can use a discriminated union or choice type to accomplish this goal. So let's say we need a way of printing out a person's name and contact information. Here's how we do that in F#. So we've got a function called print person contact details with a single input argument of person, which the compiler has inferred to be of our person type, as we've not actually told it that. In here, we perform a pattern match on the contact method field of the person record and tell the compiler what to do for each of the available choices for contact method: email, phone, and post. You can see each choice listed on the left next to a symbol that holds the accompanying data. And then on the right of the arrow, there's an expression that transforms that data into something that meets our need. Each of the 3 branches returns the same data type, in this case, a string. They actually need to because the whole thing is an expression, so can only actually return one type. And the result of that expression is bound to the contact info symbol. Finally, we write the details out to standard out using a function similar to console.writeLine. The format address and trim tail functions are helper functions to help take that list of strings in the address and turn it into a single string for us. So we've dealt with all 3 of the available choices all in one place. the complete opposite of what we learn we should do in OO. As a result, the code for handling our various options isn't distributed across our code base in multiple different files or behind different layers of indirection. The function does one thing, which is print contact information, and only has one reason to change. And we've avoided creating any inheritance hierarchies and the associated challenges we tend to try and avoid, as well as any class explosions. And what if we introduce a new contact method into the system? Well, here's the kicker. As soon as you add a new choice to the contact method, everywhere that your app consumes that type suddenly starts warning us about unhandled scenarios, so we know exactly where we need to go to cater for our new options and fix potential issues. This is because pattern matching in F# is exhaustive, and the compiler is actually inspecting the type system and the code base to figure out what scenarios you've already handled and see where you've missed something. Now, if you've got treat warnings as errors turned on at this point, then this will actually fail to compile, and you'll need to update every function that does something with contact method before you can continue. And this is exactly the sort of type safety that we .NET devs want to see. It's reducing the chance of human error. Let's take a look at some more features that help us do the right thing without too much cost and bother, and see if we can save ourselves the trouble of writing a whole bunch of unit tests while we're at it. Let's say we want to calculate the monthly repayment of a loan. If we wanted to write a function for that, we'd probably start with something like this: a calculate repayment function that accepts decimal, an int, and a double, representing our loan amount, term, and APR, and then returns a decimal representing our monthly repayment. The trouble with this is that there are several scenarios that either result in an error because the data is invalid, or we simply don't want to calculate a repayment because it's outside of what we as a business actually have an appetite for. So for example, if the loan amount is too low, then we won't make enough money. And if the loan amount is too big or the term too high, then it's just too much risk. While negative numbers and zero are simply invalid. In this version, the code validates those inputs and performs the calculation. And this works, but there's a lot going on here. And what we really want to do is prevent all those invalid scenarios at the function signature level. And to do that, we need to create our own types with our business rules encoded into those types. So let's do that now with loan amount. There we go. There's our loan amount type defined in one line of code. It's a single case discriminated union, or a choice type with only one option. And its constructor takes the raw decimal value that we want to wrap. This obviously doesn't include any business logic yet. I just wanted to demonstrate how easy it is to create your own types in F#. So to encode our business rules into this type, we can do this. So we've declared our loan amount type now has a private constructor. And then we define a function to create an instance for us. And it's in the same module, so it can access that private constructor. Try create then validates the input arguments meet our business rules. And if it does, it returns an instance of the loan amount type with our raw decimal wrapped inside. Otherwise, it throws an exception. We'll revisit this example later and look at some alternatives to exceptions. But for now, we can see that the only way to create an instance of loan amount is via the try create function. And once you have an instance, you never need to validate those rules again. You know that it meets your business rules, and that can't change because everything's immutable. The last line defines a function that allows us to extract the inner value whenever we want to use the loan amount in a task. So if we do the same with our other two inputs and apply the changes to the function, we end up with something that looks like this. It's now impossible to invoke the calculate function with data that's likely to cause errors, such as negative numbers, or numbers that we as a business don't like. And this gives us several benefits. Firstly, there's now a bunch of use cases we no longer need to write tests for. So that's less code for us to maintain going forward. The code that performs the calculation is now only concerned with doing one thing, not validation, just the calculation. It's simpler and easier to read and easier to understand. And that validation is still happening, it's just moved to somewhere else. Finally, we can no longer supply our input arguments in the wrong order when we call this function, because while the underlying values of loan amount and APR are both decimal, they're actually different types. So the compiler prevents that, again, reducing the possibility of human error. On top of that, our single case discriminated union is immutable and provides structural equality with a sensible override for toString all out of the box. So there's not any more code that's actually required for this. And because you don't have to override the default equality, you also don't have to override get hash code or not equals. And therefore you don't have to write any tests for any of that code that you've not had to write. So that's going to save us more time and effort. And last but not least, you can't set the value of a discriminated union to null. The compiler won't let you, even if you enable mutability. And this isn't just true of primitives like decimal and Boolean, it's also true of all F# types, records, tuples, F# list. Our custom types are easy and cheap to create, making a legal state completely unrepresentable, easy to achieve. So we create less error-prone code. And we have less code and less tests to maintain. So let's double back for a second to that comment about null. You can't assign a null to a choice type. And it turns out you can't actually assign a null to any F# types. The only time you ever need to worry about nulls is when dealing with reference types from the base common library, such as strings, and when doing interop with OO.NET languages. Imagine being able to write methods without the need to perform null checks before you do anything. And F# actually provides this behavior out of the box for all its own types and your custom types, which means you'll see a lot less null reference exceptions while writing F#, while also writing less code. And if we wrap our strings in a custom of type, like we did with the loan amount, with a creation method that filters out nulls, then we can again prevent nulls at our function signature level. So I don't like null. I go to great lengths to avoid, prevent, and eliminate them wherever possible, and therefore reduce the possibility of null reference exceptions. But those exceptions are not the only issue I have with nulls, because nulls are ambiguous. Does the fact that there's no data mean that there was no data to start with, or does it mean that something went wrong? Did someone miss something when they created this object, or is the data missing on purpose? But if we don't have null, how do we represent the absence of data? Well, functional languages approach this in another way with a built-in choice type, which allows us to say that this data isn't mandatory. So it might be there and it might not. And in F#, this built-in type is called option, and it's implemented using a discriminated union that provides you with two choices, a sum of t and a none. And here's how we use it. We define our user type as a record with 3 fields. Email and language are required because they're both defined with custom F# types, email address and language code, and therefore required by default. Then we've got location, which is defined as a country code type, which is also a custom F# type, but it also has the option keyword here, indicating that the value is optional, so may or may not have a value. You can also define it like this if you prefer, which is probably more familiar if you're comfortable with generics in C#, but those extra chevrons mean that the previous version is actually more common. So what impact does this have on when we try to create an instance of our user record? Well, if you try and create it without specifying a location, you get a compiler error because it's a record and all the fields are required. And if we try and set the value to null, we get a different error because the null is invalid. And if we try and set it to a valid country code, we actually get another entirely different error. So how do we set the value? option is a choice type. And if we think back to the contact method example, we had to specify which of the available options, or choices, we were using, along with the data for that choice. We need to do the same here with option type. So to create an instance with the location, we specify the sum choice and the actual location data. And then to create an instance with no location, we supply the none choice with no location data. And then when we need to use our option type to do something, as with all choice types, you need to handle all the available choices when you pattern match on the value, as seen here in getLocation. The compiler forces you to think about both the scenarios where there is data available, the sum choice, and when there's none. There's even an option module providing some common ways of working with option types. In this implementation, getLocation calls option.defaultValue, passing two arguments, the value to return if the option has no value and the option itself. And then the supplied default is then returned if the option has none. The option type provides an alternative way to model the absence of data, which is less prone to error than using null, because it eliminates the possibility of null reference exceptions, while also forcing us to think about the absence of data when we access the value. We can't simply forget about everything off of the happy path. Option.defaultValue function leads us nicely to another area of programming where functional chooses a different path to object-oriented code, and that's error handling. So in OO, it's common for us to perform lots of validation type checks to ensure that our input arguments meet our needs. If everything is dandy, then we'll go ahead and perform the task at hand. We'll construct an object or perform a calculation, for example. But when our inputs are invalid, we tend to throw exceptions, and this has several implications on our code. Firstly, you've got undocumented side effects. The fact that an exception can be thrown is not documented in the method signature. The method signature says, you give me A and B, and I'll give you C. It doesn't say, you give me A and B, and I'll either give you C or throw an exception. Exceptions delegate work to the caller of the throwing method. The responsibility of preventing the application from crashing is now on the caller to ensure that they catch and handle any exceptions, which are probably undocumented, or let it bubble up in the hope that someone else will catch it. Finally, error handling code is ugly, repetitive, and depending on who you talk to, breaks the single responsibility principle. So the OO solution is a little opinionated. It says, it's my responsibility to work out if you're allowed to do this thing. So it's my responsibility to decide what happens when I decide you can't. F# can raise exceptions, as we saw in the loan amount type, and handle them using syntax similar to try, catch, finally block. But it probably won't surprise you to hear that the functional approach offers several less opinionated solutions, which are asking the caller what to do when things go wrong, and to return a choice type representing all the possible outcomes. So if we think back to option.defaultValue, then you'll recall that the first argument was a value to fall back on if the option type being evaluated contained none. And this is a common way of delegating the decision of what to do in the event of a failure to the caller, rather than making that decision yourself. Simply have it passed in as an argument. Let's have a look at an example now. So here is some code that raises an exception. On the last line, we call findByKey function, supplying the people dictionary and the key for the person we want to retrieve. Only that key doesn't actually exist in the dictionary, so when we attempt to retrieve it, a key not found exception will be thrown. What we could do instead is this. This time, the last line calls findByKey or default, passing in 3 arguments. The dictionary and the key are the same as before, but the new argument is another function that also accepts the key and returns a person. In the event of failure, the findByKey or default invokes this supplied function, which goes off to somewhere else to look up the data using the same key. This is a technique I use quite a lot in OO code now since learning F#, and I find it ports well both in C# and Python. So let's take a look at the other technique, which is returning a discriminated union, or returning one of multiple choices. Let's say we want to read the contents of a file from disk. There are several things that could go wrong here, but let's say that we can generalize into 3 error scenarios, which are that the directory is not found, the file doesn't exist, or the file may simply be empty, which isn't strictly an error, but the content's not useful to us. And of course, everything could just be fine and the read could be successful. We can model each of those scenarios in a discriminated union like so, with one choice for each of the different scenarios. And then our read from file function can return each of those different possible values under different conditions. So our function takes in 2 input arguments of type safe string, so no need to check for null. And if the directory doesn't exist, we return an invalid directory choice. If the requested file doesn't exist in that directory, we return invalid file name. And if we locate the file, we then read the content and check to see if the array created by read all lines is empty or not. If it's empty, we return file is empty. Otherwise, we convert the array to a list, return the valid choice with all the strings representing the lines of the file we just read. And then when we invoke the function, we deal with the response. We do what we always do with choice types, and that is to deal with all the available choices in one place. Now I've chosen to cheat for this example and simply return empty strings for all of our error scenarios, while the success scenario simply concatenates those multiple lines into one string for us. So F# gives you multiple options on top of throwing exceptions, asking the caller and returning a choice type. Both these options reduce the chance of errors, crashing the application because neither raises an exception and then relies on the caller or something further up the stack to catch and handle that exception. And in both cases, particularly when returning discriminated union, you can infer from the signature of the function how it's likely to behave when you call it. The signature tells us exactly what's going to happen. It says, you give me A and B, and I'll either give you C or invoke / return Y, or you give me A and B, and I'll give you either X, Y, and Z. The discriminated union method is so common in F# that the language includes a built-in type for this very purpose, and that's the result type as seen here. It's a discriminated union with 2 choices, OK or error, and each has its own data type for that particular scenario. And here's an example of how you might see this used. I've refactored our try_create function from our loan amount type earlier. Now, instead of throwing an exception, when validation fails, we return the error choice with a string that holds the validation error message. And when validation passes, we return the OK choice containing the loan amount value that we want to use. See that the type annotations above the function says, you give me a decimal and I'll give you a result of either loan amount or a string. As a final note, the language guidelines point out that result type and discriminated unions are not complete replacements for exceptions, and that exceptions are better suited to certain scenarios, though these are generally truly exceptional scenarios rather than those that can be easily anticipated or expected. So the last big thing that I'd like to try and cover today is something very different from what we're used to in C#. But you might be quite familiar with it if you're from JavaScript world, and that is currying a partial application. So in C#, when we call a method or a function, we specify all the required arguments. We don't really have a choice because the compiler complains if anything's missing. So if we had this function in C# and we wanted to supply our add function as an input, then we need to adapt it somehow so that the function signatures match. Otherwise, we'll get a compiler error because add requires 2 inputs, while the mutator func only accepts 1. Currying is the act of transforming a function that takes n arguments all at the same time and turns it into a series of functions that all accept 1 argument. And in C#, it might look something like this, expressed as a generic extension method. I'm going to skip over the details of what's actually going on here and focus on what this gives you. So having called the curry function on our function, we can now supply the arguments individually rather than all at the same time. So applying the first argument returns another function that still requires the last argument. This is referred to as partial application. Here we have a partially applied add function which requires 1 more argument before you actually get a result. Now this all works, but it comes with some cost. And if you want to curry functions with more than 2 arguments, you need multiple overloads for those curry methods, each accepting a different number of arguments. The compiler will actually impose a physical upper limit on how many arguments you can deal with, which is 16, I think, built into the compiler. Although if you're hitting this limit, then you probably want to refactor into some sort of types instead. And lastly, you've completely bamboozled your IDE, which no longer has any idea what your input arguments and names are, because everything's so generic and we lose all useful IntelliSense. However, F# solves all of these problems out of the box because it automatically returns a new function with n less required arguments whenever you call a function with less arguments are actually required. Basically, F# is auto-currying for you. So here's the code we saw before in F#. On line 2, we supply 1 argument to the existing add function, and then this returns a new function which we bind to the add5 symbol. Add5 still requires a single integer applying to invoke a result. And you can see the IDE highlighting the method signature above. It's a function that accepts an int and returns an int. The result 2 is created by applying the remaining argument to add5. And result 3 is created when we call the mutate function, passing in the add5 function as an argument. And this all happens without the need for us to write any currying code ourselves. And any time you call a function with less than the expected number of arguments, you get a new function back, which still requires the remaining argument. Okay, but why? Why would you want this behavior, and how can we benefit from it when building applications? Well, what this gives you is the ability to apply n arguments now and apply the remaining arguments later, without losing the option to supply them all at once if we choose. And the use cases for this are fairly varied. The example we just saw is like a functional version of the adapter design pattern, changing the API of existing code to make it usable in new scenarios. It's also useful for composition. For example, we can actually refactor this code by turning each of these multi-argument functions into single argument functions to create the following, which does exactly the same, but is much easier to understand. And of course, we could turn any function into a 1-argument function using partial application, which means we can actually do this with any function. You may also have spotted another use case for this, and that's reuse. Here, filter numbers and filter special chars are both specialized versions of the filter function with the first argument already applied. They both require the final string argument for the filtering to take place. You can see that the function signatures tell us that they both accept a string and return a string, even though these functions have no input arguments declared. That's because they actually return a function that already expects an input argument. Final use case I'll discuss is what you might describe as a functional form of dependency injection. not via interfaces into constructors as with OO, but via functions. So if we consider the function on screen for fetching a customer record from a database by ID, it uses the supplied configuration record to get a Mongo collection of customers and then queries that collection for the matching customer. We want to call this function from our app in our print customer details function. But if we call this directly via module name dot function name, then we tightly couple the calling function to a concrete implementation of our get customer function, just as if we would if we'd moved up an instance of a data access class in OO. To solve this, we inject the dependency into the function instead by supplying it as an argument. Now our print customer details function accepts 4 arguments instead of 2, the DB config record and the customer ID as before, plus 2 additional functions. So one to retrieve a collection to query and the other to get the customer from that collection. Notice here that there's no reference to an interface at all, but we are achieving the same result using method signatures as our contract, which the compiler enforces. So I've actually created a type here for get customer F so that I can clean up this example and have the function signature all on screen at once. So you don't need to do this as type inference actually knows what's going on, but it can make code more readable when signatures get quite long and complicated. So this is better, but now we're supplying arguments to the print customer details function that it only actually uses in order to pass to the get customer function. And this is where partial application can help clear this up. So in this final version of print customer details, we now supply just the get customer function and the customer ID. And when we invoke the function, we get the customer back and we can access the customer details. And this is possible because somewhere else in the application, probably our composition route, which is executed as the app launches, we've created a new function by applying the first 2 arguments, dbconfig and getCollection. And our app is then using this new function at runtime when calling print customer details. Here is a unit test that simulates that process. So it's creating get customer by partially applying the config and the get collection function, and then it supplies the get customer function to print customer details. That's all we've got time to cover today, so hopefully I've been able to sufficiently demonstrate the things that I believe make F# a compelling tool and which make our lives as .NET devs easier and more productive. By writing less code and less tests, writing code that's less error prone, and also being more expressive and therefore easier to read, understand, and change. F# can do everything you can do today in C#, but it takes a different approach. If you're already trying to make everything immutable, encoding business rules into types, avoiding throwing exceptions, avoiding and eliminating nulls, favoring expressions over statements, or questioning the need for interfaces, you should absolutely give F# a go. At the end of the day, each of us is really trying to deliver more value to our customers and end users faster. And it's my belief that F# will allow us to do that. But even if you decide that F# isn't for you, then the act of learning it will give you a new way of looking at problems and therefore new approaches to solving those problems, which ultimately makes us all better devs. So I expect that once you give it a try, it will impact the way you write object-oriented code, and you'll embrace more and more of the functional features that you've been added to C# in recent years. If you're interested in learning more, I've put together a list of resources to help get you on your way, including books, videos, websites, and people to follow on Twitter for even more F# content. It's worth noting that the F# Foundation runs something called the F# Mentorship Program at least once a year. And if you're lucky enough to get selected for that, they pair you up with a mentor for at least 8 weeks, and you'll work together through some of these things as you hone your skills. And best of all, It's completely free. There's also a very active F# Slack community with lots of friendly folks willing to answer any questions you've got, so it's well worth checking out. Speaking of questions,
cool. Now, first of all, I thought that was a great presentation of covering all the salient things that got me super excited about F#, Dave.
cool.
That I've been programming since the mid-70s, and F# been like a new lease of life for me. It's got me that excited for all the sort of reasons that you've explained. It's an amazing language. I'm just surprised I never came across it earlier. I know there's a million things you could have mentioned. Just one other one that I found very good in the language was units of measure. I'm not sure if you covered that or not. But you may be able to explain that better than I could. It's certainly reduced a lot of errors in my code by using units of measure.
Yeah, I've used it once, but not an awful lot. So for anyone else that doesn't know what units of measure are, they basically allow you to sort of decorate your primitives, such as numbers, and you can say that this particular primitive is, say, it represents a mile, and this primitive, whilst it's also, let's say, an integer, it in fact represents a yard. And then it won't allow you to mix the two together, so you can't add a yard and a mile together implicitly like you would with just 2 ints. And these units of measures, these decorations, they actually completely disappear at compile time. They're just syntactic sugar for while you're developing. They just dissolve, if you like, when you actually compile. But yeah, I've only actually used them once or twice, Paul, and I did it just because I hadn't used them before, and I wanted to get my head around them. But yeah, it's something I wanted to try and cover, but again, there's a lot to cover, like you said, so didn't make it. There's some decent articles from Scott Vloshin on his website for more complete examples. So if people didn't notice the footer notes, then there's extra snippets of info in there as well.
Now, that's a fantastic website for fun and profit. Very good. Right, yeah, thank you again. Excellent presentation.
No, I enjoyed it, weirdly.
I've got a question, if you don't mind. Just getting back to your read from file example.
Yeah.
Where you've got a couple of ifs returning whether the directory exists and whether the file exists.
Yeah. I'm not particularly happy with that implementation, by the way.
Yeah. So I'm just wondering. So in C#, I think Rider would offer you to invert the if, so you've got the escape condition nearer the top.
Right.
If you were to do that, your if depth would be only 1 deep, I think. Is it possible to, where Rider in C# offers to get rid of the else, if you have an if something return, the else block, the else keyword becomes redundant. Is it possible to do something similar in F# so that your flow?
I'm going to give the consultant's answer, which is it depends.
Okay.
As a rule, if expressions don't allow you to exit early, so you have to handle the else as well, and that's because it's an expression. So by default, an if expression is like a ternary in C#, so you have to handle both cases. There are edge cases where that is not entirely true. Like I can't really explain because I've not really done that many, but I guess the short answer to your question is no. because you can't.
In theory, it should be you should be able to not have to add it into the else block. because where else could it go? I was just wondering with the, I guess it's down to the language support, isn't it?
Yeah, the default way of handling things would actually be to pattern match.
Okay.
It was a bit of a weird example, but you would usually pattern match on stuff rather than do an if expression. And then something else which didn't quite make it in is that pattern matching in F# is it's massively impressive compared to pattern matching in C#. So that the stuff that I didn't even cover includes things like active patterns and partial active patterns and things like that that allow you to write your own little functions that you can sort of match on in your pattern matching. That makes it really, really expressive. I'm not even doing it justice by in the way I'm describing it here, but the world of pattern matching in F# is, well, other people have done talks on it for an hour and a half, you know, and barely scratched the surface. So, but yeah, I guess the short answer is no. And to be honest, if isn't the usual way you do most things by default anyway.
Okay, fair enough.
So in the code repository, I actually included some C# examples of, I think I've done a interface method, an inheritance version, and an F# version of the contact method stuff that we were talking about. I didn't bother implementing the God object, obviously. Didn't want anyone to think that I was taking that seriously. So yeah, actually in the latest version of C#, it's actually not too difficult to do with inheritance. You get a very F#-like syntax. It uses inheritance.
Got another observation. I'm not sure whether you mentioned it at the time, but it occurred to me that the option type with some or none is actually a discriminated union itself.
Yeah, it is. Yeah.
Yeah, and the same for, was it the result type later on?
Yeah.
I've just got a more general question, Dave. Done a lot of Java programming as well, and sort of went into the object-orientated paradigm pretty heavily and bought into it all. And functional programming is still relatively new to me. I'm just wondering what you feel about the whole object-orientated paradigm now that you've got into the world of functional programming.
Yeah, it's a great question, actually. As I kind of intimated towards the end, it's very much affected the way that I write object-oriented code now. So the project I'm on at the moment, well, it helps that it doesn't have any downstream dependency. So it does everything it needs to do in its own library. And so it is pure functions all the way. It calculates based on its inputs and it returns the same output given the same inputs. But partially due to that, and because I knew that it'd be like that when I started the project, I decided to try and do everything without interfaces and make everything static, so that I could try and use pure functions in C#. And it's actually worked really well. The code base, I feel, is really clean, easy to figure out what's going on, easy to sort of change things about and plug new functions or functionality in at various different points, because you've got pipelines, different functions being called at different stages. You've got data coming in at the top and you execute function after function after function with the data traveling through the pipe and then being mutated or changed as it travels along. And you can just plug in new functionality really simply. And debugging's easy. And reading it and navigating your way around is really easy. And you don't have the overhead or the obfuscation of interfaces, which I've sort of questioned for a while. I think I first started questioning it after I went to a talk or a workshop with Mark Seaman, if anyone knows who he is. told me off. No, that's not quite right. But he was talking about interfaces that only have two implementations, the real one and then a stubbed one. And of course, you just don't need to do that anymore. You can inject mocks or stubbed versions of functions using just function signatures without the need to create interfaces. And it achieves exactly the same. And when you start to think about the solid principles and single responsibility and things like where you break up the interface, if you take those principles to the absolute nth degree, what you end up with is single functions that do one thing. So you could end up with an interface with just one method on it that does one thing. And at that point, you've got to ask yourself, what value is the interface giving me anymore? It's just this extra layer of indirection that you could achieve with just functions. So that's what I'm doing in the project I'm working on at the moment. It's a great learning experience. I found it really easy to navigate, really easy to test. The only concession I've made and introduced an interface is because it's a library that's going to be by many other consumers. So to aid with their integration into their projects, I put the main API of the surface area of the library behind an interface and built a stub so that they could, mock out their tests if they like with fake results. But I only did that to make their lives easier for what they're expecting, really. So I don't know, hopefully that answered your question in a long-winded way.
No, that's good. Yeah, it sort of mirrors a lot of my thought. I've sort of had a few doubts on the whole overall paradigm myself, not mainly because of the complexity and, trying to interpret other people's code. When there's lots of interfaces and abstraction. Yeah.
I'm still down with things like injecting your dependencies, or that even when I'm not using everything as static classes, I will inject classes into other classes as dependencies, but I'm not necessarily going to wrap them behind an interface unless I see a value, because doing things by convention doesn't necessarily make things easier. There's one particular service in our team that I always get confused around because there are so many different versions, so many different implementations of the same interface. And trying to work out what is actually executing whilst you're debugging or trying to figure out, where this error is coming from, for example. It's infuriating, actually. Which one is actually working? What is actually executing this code? It drives me mad.
That's why I resort to lots of the debugger.
I actually made the same experience. Thank you, Dave, for your presentation. I think it was really great, especially for beginners. It's really good, and I hope you don't mind use it as a reference. Yeah, it's a good overview. And my experiences as well, I'm not really a .NET guy, but I work for a startup which had a rather big C# kind of code base with, solid principle, onion architecture, dependency injection. And don't get me wrong, I'm a huge fan of dependency injections. I learned it back in the days in Java with Spring and so on and so forth. And I found it really cool and exciting. But now I found in this code base, it was like every single class was injected and there was no alternative for this class, just one implementation. And then you had a configuration error, and obviously the compiler doesn't help there. So you have to basically pass a log file and you see nothing. You really have to have the experience why it's failing. And what you presented really rightly, like partial application gives you full compiler safeness, because in the end, anything you pass into it can't be resolved. The compiler would know at compile time. and not at runtime. And this is a huge saving in terms of debugging and so on. And the other thing I found, if you take down the root of onion architecture, you create a lot of one class files, which are really just, or interfaces with just instrumental, but they don't have a bigger meaning or purpose in there. And then to trying to debug along, you have to basically follow a stack trace, which is humongous. And then you come to something like Elm, for example, right, on the front end side, which is basically a derivative of Haskell and has this really nice error handling, really nice readable errors. And you think like, oh, it can be so easy. And this is actually how I got into basically F#, because I was at the Elm meetup in London, you know, and one of the participants said, oh yeah, we do this the same in F# and with Fable use in production. And I think this is a huge advantage of F#, which unfortunately doesn't get that prominent, you know, publicity. There was Jet.com, one of the killer apps in F#, and they made a comparison in the beginning between C# and F#, whether to implement a whole new e-commerce platform. And they found out that I think the amount of code they needed in C# is tenfold. Jet.com have been bought by Walmart. They don't do F# anymore, just Scala. And I think what's now lacking, in my opinion, and you know, I've been to the F# conference like 3 years ago, I suppose, in London, and it was really great conference. And Don Simon is really a character and, you know, an asset. But what is missing the momentum, and maybe also the support of Microsoft, and probably a killer application. I just explained it that way. In Elixir, for example, which I'd done before, they have Phoenix, which is an amazing application framework, which can handle up to 2 million WebSocket connections per second. And, you know, that's a story to tell. And this is where it gets momentum. And I'm getting a bit frustrated, or I have the fear that F# is losing that momentum in the same way I see it with Elm, to be honest. I don't know what's your experience on that.
I don't really know, because I've almost never written any F# with anyone else. I've done a bit of pairing with Ollie once, and I've done a couple of pairing sessions with some other people that I found on the F# Slack community or on Twitter and things like that. But you know, I've never done any commercially. I can understand the fear. I can understand the frustration from a point of view that it seems to be the least favorite child in the Microsoft stack. But I think from my point of view, the community is amazing. And the amount of stuff that they're knocking out just seems fantastic. I actually really want to get involved with trying to have a look at some of this Safe Stack and Fable stuff. So I sort of mentioned it in the talk, but I've never actually done any of that. I've done the Safe Stack sort of dojo example on the website. I've not done anything more than that. But the idea of generating JavaScript from a type-safe language that is incredibly powerful, like F#, sounds fantastic. But I saw at Skills Matter, there was a guy from the Python world that they're doing the same with Python. They're actually transpiling their Python code from F#. Again, I've not actually seen that talk because it's not publicly available yet, and I didn't have a ticket. So I'm waiting for that and the one from the other Roman about in defense of exceptions.
Can I just comment on a couple of things you said, and also to Volker? First of all, I wholeheartedly agree about the F# community. I've just found it absolutely amazing, especially to newcomers. I've been in some communities where, you know, newbie, if you're a newbie, you either get out or you're not a newbie for long, because you're sort of attacked over your questions. No, I found, you know, and the amount of resources is great. Just to answer, I'll pronounce your name Volker, I hope that's correct. Being retired now, I have the luxury of consuming a lot of books and videos. You know, I only ever sleep 4 hours a night, so probably the rest of the 20 hours is on learning something to do with IT. What I found is if you do any, like, you know, the .NET channel, you know, you go and watch all the videos and all the fantastic material that comes out from people, it's all C#, you know, there's nothing F#. If you look on the video YouTube channels for F#, the ones they have, everything's like 2 years old. So unless you're really actively searching, and you've got that great list that you provided, it is hard to find new material for F#. I would disagree. I would say VB is the redheaded child for .NET. So let's just
has been abandoned, right?
Visual Basic. Let's hope F# doesn't go the same way as Visual Basic. But I agree that you know, if you, and I'm new to .NET as well, if you're starting to get in the .NET ecosystem, you really think there's only C#, because everything is orientated towards C#. And then when you do discover F#, you think, wow, this is incredible. Why didn't I know about this sooner, sort of thing?
Yeah, I think another thing to consider is the fact that generally in industry, when people look at functional, obviously F# wouldn't be the first name that will come forward. There's a lot of other natively functional languages that developers would normally gravitate to. So the likes of the Elixirs, Scala, even Erlang, which was built to support telephony systems on Ericsson, and which is what WhatsApp is built on. So generally, people, if people learned functional language and wanted to go in that direction, they would normally go for the pure ones. And whenever anyone heard anything about .NET, certainly from a learning perspective, it would be the usual suspects, the C#, the VB.NET. I suppose there's now a gap in the market for, as you mentioned, Paul, where the videos you could find on F# were like 2 years old. Maybe there's now a push for people to engage more in those arenas. So if maybe who knows, maybe I'll start learning F# and maybe start putting my catalog in my learning experience.
That would be a great win for me if that happened off the back of this.
There is a demand actually, you know, from the developer side, because so I was in the Elixir community for quite a while, and it's also a very amazing community, also very active. But there were a lot of developers also feeling like we actually want to use a strong type language, and obviously Elixir and Erlang are dynamic typed, and you know, building complex domains, for example, is where F# shines. And you know, this is why banks are using that for very complex mathematic domain models. Actually, going towards a data science. And I kind of had the hope that, you know, Microsoft can push F# as an alternative in the long run to Python, as a strong typed and performant and concurrent language, but it doesn't seem like this. The question is, where does F# find its niche? Because yeah, when it comes to pure language, the first thing comes to my mind is Haskell, obviously, which is a different ball game altogether. I think there's a very good case for F#, but it just needs the skill application and the support.
Yeah, I think to answer that question, from what I've seen other people in the community saying, is that F# is more of a pragmatic solution, a sort of a hybrid of OO and functional. You can choose the paradigm that fits the solution best, but you can use one language to achieve both. So it's a pragmatic language.
It also doesn't help that in recent versions of C# they've been implementing or adding functional features like pattern matching and records and basically building on top of what they've done with lambdas and delegates. And then it then means that a lot of people doing C# at the moment probably will think, why learn F# when I can do some of that functional stuff with C#? But it doesn't take away the fact that to build a functional application with C#, you might end up still having a bloated application.
Yeah, if you've ever written funcs to chuck around and do some of what we've sort of demonstrated today, then obviously type inference is better with funcs than it is if you use standard methods, but it's still quite clunky or noisy compared to what we did today with F#.
Dave, have you tried promoting functional principles at work? And what's your experience with colleagues?
So yes, I've done some pairing and some sort of sessions like this in the office, and what I generally find is that it's the old guard are less receptive, and the younger generation coming in, the juniors, lap it up. They learn functional techniques a lot easier, in my experience, which is limited, than they do OO.
Have you tried using language libraries like language extensions?
Yeah.
Have you found resistance, like this guy doesn't use interfaces, so he's very strange?
No, I've not come across the why haven't you put this behind an interface thing yet. I have had a discussion. I was quite proud of myself when this happened, when I had my first "this code's too generic" conversation, because I think the argument was around, why have you called this input argument this? It doesn't really mean anything. And the answer was, well, what should I call it, given that it's so generic and it could be anything? So I think I just called it function or thing to do or something like that. I was like, well, what should I call it? Because it could be absolutely anything. That's why it's got a weird little name, because I don't know what to call it. And in functional languages, like with the generate n items function, you'll often see input arguments that are just f and n and things like that. And that's because they're so generic, you can't possibly describe it in a way that says what it is, because you can't possibly hope to know what it is, because it's down to your consumer what it is. So it was an interesting conversation when I had that. I'd heard other people in the community sort of talk about these situations, and then my first one happened and I was like, yay, I'm a functional programmer.
I've got another question about type inference, if you don't mind. Just going back to, I think it was probably fairly early on in your slide deck, where you had, I think you had a multiply function and an add function. The inference can work from both ways, can't it? I guess, because it depends on what you're calling it with as to which type it will handle, but also presumably it depends on where you used the multiply operator and the plus operator. Presumably the types you pass in have to support those operators.
Yeah. Add, it knew they were in because of the plus, basically. But I think what you're kind of leading it onto is that you could, in theory, call add by supplying maybe decimals instead of integers. I'm not sure if that's necessarily true. I mean, because F# is a stricter language, so it doesn't generally allow implicit conversions between types. So you have to do things explicitly. But it does handle generics in the same way that C# does. So you could make a generic version of that where it would handle multiple types in different ways.
Your add method, I noticed that the IntelliSense or whatever it was had said it was an int to an int. You actually have to pass an int to it. If you were to try and pass a double or whatever, it would fail you.
I believe so, but I'd have to find out, to be honest.
Yeah,
I think, Andrew, the reason it's int is it's a sensible default. Type reference looks at the types defined above the method. So if it cannot find, it just takes a sensible default. But if you want to use decimals and ints, then you have to do it through generics.
okay.
I actually was pretty much intrigued by this kind of meetup in London on domain modeling, and then I got into the book of Scott Lushin you mentioned earlier, and actually he's doing on regular basis at the Domain Conference Europe workshops on domain modeling made functional, and I can only recommend it. It's really amazing because he starts off describing the problem word, scribbled down in pseudocode, and then translated in F# code, which almost looks the same. And this is, I think, where F# can really shine. And my hope is, because in my current company we use TypeScript, and there are a lot of similarities in the way you can use types, and it's not as powerful, obviously, as F#, but you can do quite a lot. And maybe this is where this domain-driven gets basically a new popularity through TypeScript. And then people who want to advance maybe, find a path to F#, like some people find a path from F# to Haskell if they want to go to pure functional programming.
Yeah, I know what you're saying. The Scott's book is, again, it's one of the techniques I'm actually trying to implement in C# at the moment with those pure functions, creating types that sort of lock down at a signature level what you can actually send in. So all your invalid, you can't do divide by 0 because I've removed the ability to send a 0 in for that particular parameter, for example. The fact that it's a book about F# shouldn't stop you from buying it if you're looking for a decent book.
I actually would go as far and would recommend to any software engineer as one of the foundational books. Also, he has this approach for handling errors, and you mentioned basically the result type. Yeah, and you can chain those different calls maybe a software does during the lifespan of a request. You can chain the different errors with this approach he calls railway-orientated programming. And that the concept has been translated in so many programming languages like C#, Scala, Java, Python, and so on and so forth. And I think this is also a very good way to apply functional programming, even in another language, which is maybe rather object-oriented.
Yeah, I agree.
Yeah, I agree. I've read that book as well. It's fantastic. So I wholeheartedly think his whole website is great, that for fun and profit.
Yeah.
Yeah. So at this workshop at the Domain Conference Europe, I met some guys randomly, well, not by chance, I suppose, at the workshop of Scott Lushin from Jet.com, and who had the biggest F# source code at that time. And they said they used his blog post basically as a reference for everything.
So one last thing that you might want to mention, Dave, so
yep.
everyone on, is what I found very strange when I first got into F#, and I thought this is crazy, but now I realize it's critical to type inference and all the goodies that the compiler does. And probably the compiler is one of the...
I know what you're going to say, yeah.
Yeah, the compiler is one of the best that I've come across in terms of helping you instead of hindering you. I work in pure C, so that gives some idea of how compilers can hinder you. But yeah, the layout of functions and files in F#. You want to quickly touch on that? It's actually helped me read code a lot better.
Yeah, so I saw a talk by Isaac Abraham, and he described this initial reaction when you hear what I'm about to say as recoil, and you sort of go, ugh. But actually, once you've spent a little bit of time getting used to it, it seems completely natural, and you actually look back at that recoil and go, yeah, that was an overreaction. There's nothing wrong with this, and it's making my life easier. So what Paul's getting at, unlike in C# where you can define stuff and call stuff in any order, so you can reference a method that hasn't yet been declared in a class, for example, you can't do that in F#. You have to declare something before you can then use it further down. So everything points up, basically. All rivers lead to the top of the module. And it also means that if you've got a solution with several different modules in, you can also only reference modules that have created before. It's a bit weird when you first start, but then it's just natural. Get over it. And yeah, it means that regardless of where you go in the world, any company, any project, every single code base all works the same way. You start from program and it'll go into a module and it will flow upwards. You know the thing that you've just called from the current method has to exist above somewhere. Just has to. Either that or it's passed in as an argument. The point that Volker made earlier about a pseudocode that's easy to read, that actually looks remarkably, if not exactly the same as your actual production code, that's a really good point, and something that I probably ought to be stressed. But Scott, again, has a talk about flesh out the concept of the domain in sort of like a meeting where you've got all the different your stakeholders and things like that. You come and sit down and talk about the problem domain, and instead of writing things on post-it notes, they actually just code the types. That as you talk about them, they create the types, and you end up with a file with all your different types in that describes your domain. And then you can hand that to your BA, and it's written in plain English, and they can just understand it because it's not complex. You don't have things like decimals and ints necessarily. You've got things like loan term, APR, and things like that. And you've got all these types that mean something in the real world, it means something in the domain, and they're like sort of low noise that you can just show to your non-technical people, and they can read it and understand it. And he's got a talk where he creates a card game, describes the complex business rules of the game, but then shows you the code of these types that he's created, and it's, you can understand it instantly. And that's probably one of the greatest underrated powers of F#.
Yeah, especially because you can save a lot of boilerplate code for unit tests, for example. It doesn't mean you don't have to write unit tests, but for a lot of stuff which is, which you assume that should working without a question, you just have your code and compile it, which is amazing because, like I said, I still love Elixir as well because, there's really robust language and so on, but it's dynamic type, and you always have to write enough tests to cater for every kind of scenario.
To the like unit testing JavaScript, You've got to write a test to make sure the argument's not a null. You've got to write a test to make sure it's not undefined. And then you've got to check that it's inside your business rules. But you compare that to C# and you'll write less tests. You compare that to F# again, and you'll write even less tests.
What's missing for F# to become much more popular? Is it the killer app? Is it basically a framework? Is it maybe a certain drive in the community to reach out for a broader audience?
You know, you've got to reach a certain critical mass. I don't know, because I don't really do enough of it to be able to comment, but there's plenty of F# jobs out there. From my perspective, like trying to introduce it at my company, I'd have to do some sort of language proposal and start convincing individuals at certain decision levels, you know, and that's not an easy thing to do in a big company. I imagine it's easier to do in a smaller company.
It was a struggle for me, even from a C#.NET perspective, to convince decision makers to allow us to build a new solution for a project using .NET 5. There was the argument about, oh, the community, the current community of developers have been working with framework 4.8. So eventually we're going to have to move away from that. And it's still .NET. So what's the obstacle? Yeah, there was a lot of to and fro. So I get that thing you're talking about with respect to if it's depending on the size of the organization, those kind of decisions are sometimes taken out of the hands of the people who actually use these tools in the first instance, because they then talk about things like budgets, skill levels, and things like that. So yeah, in a smaller scenario.
And the size of the pool of developers that are able to use this stuff, which I think is going to be one of the greatest hurdles, which again is that critical mass thing. But I guess one of the things that you can't really quantify is how things scale, because most of us in the world of cloud anyway, you can scale your application horizontally, vertically, whichever way you like, at the click of a button, or even automatically. So going faster or handling more is easy to do. Compute is easy, it's cheap, right? But you can't scale your team in anywhere near the same sort of velocity that you can as your app. So we often prioritize things like performance and sacrificing readability for performance, and then punish ourselves or lose out by making code harder to read and therefore harder to understand and therefore change at the cost of performance, which actually we might not even need, because most of our apps don't really do that much. And even if they did, it's cheaper to scale the product than it is the team. Given that F# is really expressive and easy to read, you probably, even though the F# pool of developers is smaller, you'd probably be better off because you'll get more done. I can't prove that because I've not done this commercially, but that is the vibe I get both from doing it and hearing the rest of the community.
But there are companies out there using it in production, like for example, Kaggle, right? As far as I know, they wrote their whole platform in C#, and now they rewritten like 40 or 60% in F#. And Credit Suisse, they use it for model scoring, very complex domain models, and where they and these examples should be more prominent. I haven't tried, or I haven't convinced yet any developers using F#, but I did it in a startup for Elixir, and you know, I've been through the whole journey. I know what you're talking about. It's really hard to convince the management or also, you know, the coders. But then once you get them excited and you can find a very niche use case where it shines and where it's really hard to do in any other language. With F#, that's probably domain modeling. With Elixir, it's more like this resilience, you know, like, for example, we use it for WebSocket connections. And then you have to build up a, you know, an internal training path. But we found out what, you know, was first a downside, that we can't find many Elixir developers on the market. And the management was poking us on this all the time. It turned out to be basically an advantage because, you know, as a small company, you can stand out suddenly. You don't have the average C#, Node.js, or whatever developers. You're search more likely developers who learn different paradigms and maybe more skilled.
This is another thing that I can't quantify, but again, as a general vibe, it seems that a lot of the really good C# devs that I know go to F# and it's a one-way street. So yes, there's a big pool of C# devs, but actually a lot of the quality is over here in this smaller pool. I guess it depends if you're a number of bums on seats kind of company or a quality of bums on seats company.
True.
Okay. Thanks so much, Dave. That's been fantastic, and it's certainly been one of the hottest debated .NET Meetup presentations I think we've ever had. So really good presentation, really good topic. And
Thank you.
thanks everybody for pitching in. It's been really, really, really good. Thanks for all the resources you've put in the comments, Dave. I'll make sure that that goes onto the Peterborough.NET Meetup chat. Thanks everybody for attending.